Hey there, awesome physics students. Let's talk about Newton's third law. In your textbook, you'll find lots of different precisely, carefully worded definitions for Newton's third law. I want to use a slightly more, less precise definition, but one that may bring a bit more meaning to it. Newton's third law is the so-called action-reaction pair force law that you've probably heard of. My definition is this: it's you push me, and I push you back. Okay, and so the idea for this is that you have two different objects and they exert forces on each other. Okay, so let's do a quick example here. Imagine you have a very heavy book that's resting on top of a table. Now, in previous videos, we'd learned that when we think about the forces acting on an object, we have to think about just the forces acting on that one object. So let's make our object the book, and the book is touching the table, and so that's going to exert a contact force, a normal contact force, perpendicular to the surface. In that case, the table is the agent and the book is the object. Newton's third law here says that if the table puts a force on the book pushes back on the table. So the table then is the object on the other side of this, and in that case the agent is the book. Okay, so a key part of this is that with third law pairs, and I call them pairs because they always exist there's two different forces, and a key thing or property about them is they're going to be on two objects. Okay, for example, in this example, both of the forces are not acting on the book. There's one force acting on the book, that's one object, and the other object is the table. The other key thing is you notice these are both normal forces, both normal contact forces. So in this case, they must be the same kind of force. Okay, and what do I mean by that? That means that you're not going to find action-reaction pairs be, let's say, the normal force on the book and then the gravitational force on the table. Those are two different kinds of forces. It's always going to be the normal force on the book and the normal force on the table, or gravity on the book and then gravity on the earth, or friction on the book and then friction on the table. Okay, that's what I mean by same kind of force. Let's do another quick example here. Imagine you have two people on ice, and one is huge, like a professional wrestler, several hundred pounds, and the other person is a child, really small, like 50 pounds. If these two people push off on each other, they put a force on each other, so there are two forces on two different objects, and of course the professional wrestler is going to have some acceleration away that's pretty small, and the small child, is going to have an acceleration that's pretty big. But what this says is that the forces will be equal in magnitude and opposite in direction. So that means if the child puts a big force on the professional wrestler puts the same size force on the child. This seems to violate our intuitions, though, because it seems that the force on the child should be a lot bigger because their acceleration is bigger. Well, please don't confuse the effect with the cause. The effect is very large on the effect of the acceleration is very large on the child, and the effect of the acceleration is very small on the wrestler. But the cause is the same. And the way to see this is that the force on the child is a certain amount, but the mass of the child is very small. So there's this property that's wedged in between these, and the corresponding acceleration because the property is so small, the corresponding acceleration is going to be very large for the child. Whereas for the professional wrestler, the force, is the same size, but the mass of the professional wrestler is so big compared to the mass of the child, and so that means the effect is going to be very small. All right? Hopefully this helps you understand some of the basics about Newton's third law.